Welcome back to the lectures in chemistry and the topic of atomic structure and chemical bonding. My name is Mangala Sundar and I am in the Department of Chemistry, Indian Institute of Technology, Madras. Definition of what is known as the perturbation free Hamiltonian, or in the language of quantum chemistry and physics it is perturbation, the definition of zero order Hamiltonian. Recall at the very last part of the last lecture I introduced a parameter called lambda. The lambda referring to the smallness of perturbation, so that if the perturbing interaction is expressed by H1, the Hamiltonian H1 as the perturbing or perturbation Hamiltonian to a perturbation free Hamiltonian of the molecular system called H0, okay, H0, which is zero order perturbation free Hamiltonian, then we write the total Hamiltonian as H0 plus lambda H1, keeping the parameter lambda as a parameter that helps us to order the contributions in a series. You recall that I have been saying that the perturbation theory provides you solutions in the form of infinite series, and therefore we need to find out what is the most important correction, what is the less important correction to the total energy, and what is, and so on. So to keep that ordering clear, we use a parameter lambda, and of course when we need the final result we can always set lambda is equal to 1 for getting the energies. So in a sense it is also like the convergence parameter. The smallness of the electric field, the smallness of the magnetic field, the smallness of the external electromagnetic radiation if you have a time dependent perturbation and so on, all those things are represented by this mathematical parameter lambda, which of course is set to 1 at the end, so that this goes to H0 plus H1, which is the solution that we are looking for acting on some psi, giving you an E times psi. To do that we keep this lambda in between and then obtain the solutions in the form of lambda, lambda squared, a power series in terms of various powers of lambda, and then we can order these perturbation corrections. Okay. So let us do that by first writing down what we are supposed to know before we proceed towards solving the problem. Okay. We are supposed to know the H0, that is the field free, the perturbation free Hamiltonian and its solutions. Psi n0 to indicate that this is the solution of the field free Hamiltonian or the perturbation free Hamiltonian, and the energies are En0, psi n0. Okay. Please remember that there are many solutions. N can be 1, 2, 3 etc., like in the case of a particle in a box. N can be 0, 1, 2, 3 in the case of a harmonic oscillator, or as is in the case of hydrogen atom, N can be 1, 2, 3 etc. So this is a quantum number we will generally represent by the lowest value. For harmonic oscillator this will be 0, but it does not matter, we are only doing a notation, we are only representing it by a notation. So we have many solutions and many energies, and the requirement is that En 0 is not equal to EM 0 when n is not equal to m. Okay. That is, it says the states are non-degenerate. The problem of degeneracy comes in when you remember particle in a two-dimensional box, where the first time you come across the degeneracy, that you have two quantum numbers n1 and n2, and the wave functions are associated with the 2 degrees of freedom x and y, and if you interchange n1 and n2 you still have the same solution, but the wave functions are different, therefore they represent two different quantum states with the same energy. We preclude, we do not include such states in our calculation at the moment. Okay. So this is for non-degenerate states. Likewise, in the case of hydrogen atom, if we have to look at the degenerate states like the 2s and 2p, the 3 2p states, or the 3s 3p and the 5 3d states, we will have to do it slightly differently. So we will not worry about such problems at the moment. We will consider only states which are non-degenerate. Therefore, we are supposed to know the 0 order Hamiltonian, the solution to the 0 order Hamiltonian, the wave functions, and the solution, the energies, the eigenvalues to the 0 order Hamiltonian. Now, we are also supposed to know the perturbing Hamiltonian. I mean, we must know what is the disturbance due to and the form of the disturbance. Our objective is to calculate the effect of this disturbance on the wave functions that we already know, and then obtain corrections to the energy. Okay. So we know this, and therefore the question that we are asking is H0 plus lambda H1 on some wave function psi n, because there also you expect many solutions to the total Hamiltonian, but this psi n is not the same as the other psi n zeros that I have written down, except when lambda is equal to 0, because at that point you have only the 0 order solutions. So we have En, this E is again different from the E zeros, and psi n. So this is the solution that we are looking at. Okay. We want to know the psi n, we want to know the En. We know, sorry, let me not put a tick mark because it's not something that we know already. We want to know the psi n and we want to know the En. Okay. This is known, H0 is known, H1 is known, and therefore we are looking at the solutions. Okay. What are the steps? First, propose. Okay, I am going to be non-quantitative in the sense I won't prove mathematically certain results which are needed for this purpose, namely the convergence of the perturbing series and so on. I will not do any of those things, but let me propose, based on some simple logical argument, that En can be expanded in the form of a power series in terms of the parameter lambda. Okay. So that we will write En as En0 when lambda is 0 times lambda times a corrected quantity En1. This 1 refers to the fact that this is to the power lambda, associated with to the power lambda, to first order in lambda. It is lambda square En2, meaning that this correction En2 is the second order correction to the total energy, because it is associated with lambda square. Ultimately this lambda will have no meaning, no significance, but now we have a way of finding out the most significant correction, the less significant, and so on. So we will keep this as a parameter, lambda cube En3 plus and so on. In general, if you need to calculate beyond En3, En4, En5, etc., my first reaction would be, why use perturbation theory? Why not think about some other method, to more direct method to obtain the energy? Because if you have to obtain many correction terms to the perturbation series, then it's probably that probable that the perturbation series is not a very effective method. But that's my personal opinion. Okay. People do obtain several orders of corrections to this, and there are programs which would calculate some 10th order perturbation correction, 13th order perturbation correction. I mean, I do not understand the significance, but that is because I do not understand it. Okay. What about the wave function psi n? That also we will write in the form of psi n 0, the in the absence of perturbation the solution plus lambda psi n 1 plus lambda square psi n 2. These are corrections to the wave function. This is called the first order correction, this is called the second order correction, first order correction. Second order correction, plus third order if you wish, psi n 3 plus so on. You see that the values of En and psi n are En 0 and psi n 0 if the perturbing Hamiltonian is not there, which makes sense because that is what we have assumed, and therefore we are adding correctional quantities, corrections to the exact value in the form of these, and our objective is therefore to obtain this one, sorry, En1, En2, maybe En3, but I will not do it in this course. In this I will probably give it as an assignment. Obtain possibly psi n1. We may not even need to do psi n2. So you see that I would only explain the method to determine the first few terms, and then of course you can carry out the analysis yourself for other terms. Okay. So we have a proposal for En in the form of, let me highlight this, we have a proposal for En in the form of this. We have a proposal for psi n in the form of this expansion, and what other properties do we need to know in order to make use of this proposal? Let us look at the solution in the absence of perturbation, namely H naught psi n 0 is equal to En 0 psi n 0. Okay. Now these are wave functions, but if I have to use this in a formal way, I would rather write H naught using the ket notation psi n 0, giving you En 0 times psi n 0. Okay. Okay. This is the Dirac's ket notation. Ket. So let me keep this in parallel. The wave functions or the eigenfunctions of the Hamiltonian H naught satisfy orthogonality properties and are also assumed to be normalized. Okay. What it means is that in some coordinate system in which it is expressed psi n 0 tau, the coordinate can be x or xyz or r theta phi in the case of hydrogen atom, whatever is that, it is represented collectively by this symbol tau, psi n 0 star tau, psi n 0 tau, d tau is equal to 1. This is the normalization property if we want to interpret the wave function squares as probabilities of finding the system in certain coordinate space and so on. Therefore this is assumed. Okay. If it is not, we can always find the normalization constant and make sure that we use only the normalized wave functions. Okay. The other property is the orthogonal property, namely psi n 0 star tau, psi m 0 d tau is delta n m. This is Kronecker delta, which means delta nm is equal to 1 if n is equal to m, is equal to 0 if n is not equal to m. Okay. Therefore, the wave functions are orthogonal to each other. They are normalized, they are orthogonal to each other, and these examples are already known to you from particle in a box, that the wave functions psi n and psi m, if you calculate the integral dx between 0 and L, the length of the box, if you calculate that, you see that these wave functions are, they cancel each other. And likewise the wave functions have been normalized, and therefore that is how you got the normalization constant, that root 2 by L, where L is the box length as the quantity preceding the wave function. So we will use these properties, and the corresponding ket notation for these is psi n 0, psi n 0, the bracket is 1, and for this one it is psi n 0, psi m 0 is delta n m. Okay. So let me highlight that. This is the bracket notation for normalization, and this is the one for the orthogonality of the wave functions. Okay. So keep these in mind, and these things are needed when we use this proposal for the energy En that you have highlighted here, you have it highlighted here, and the proposal for psi n, when we substitute that in the Hamiltonian and start solving the Schrodinger equation. Okay. So what I am going to do is to write down the two equations that we need, the one equation that we need to write, namely H naught plus lambda H1, and now we shall write the wave function as we had proposed, namely psi n 0 plus psi n 1 plus psi n 2, there is a lambda here, there is a lambda square here, plus so on, and we shall write this using the energy expression that we have proposed, En 0 plus lambda En 1 plus lambda square En 2 plus acting on or multiplying the wave functions psi n 0 plus lambda psi n 1 psi n 1 plus lambda square psi n 2 plus so on. Okay. So this is nothing other than the equation H psi n is equal to En psi n. So what does this mean in English, in words? What it means is that you are obtaining the wave function psi n, one of them, which is a correction to the 0 order wave function psi n 0, again one of them, in the presence of the perturbation, by including all the other terms and looking for their explicit expressions. So the perturbation correction that we obtain, we are obtaining sequentially correction to each and every 0 order wave function and to each and every 0 order eigenvalue. Though this is symbolically n, this is essentially H psi 1 is equal to E1 psi 1. So we have to solve a set of equations for psi 1 and obtain E1, again many terms. H of psi 2 is equal to E2 of psi 2. Therefore, if we have pictorially, if we have, for example, for a Hamiltonian H naught, we have a whole series of energy levels given by E10, E20, E30, E40, 4 0, these are all 0 order corrections, 0 order wave function, I mean eigenvalues, not corrections, 0 order eigenvalues, and the corresponding wave functions are psi n, psi 1 0, psi 2 0, psi 3 0, psi 4 0, and so on. Now how do these things change when we have a Hamiltonian H naught plus lambda H1? Okay. How do these energies, does this energy go up or go down? Does this energy change, again go up or go down? Draw this. We don't know, we have to find out. In the presence of H1 these energy levels are altered. What about the wave functions themselves, which you call now as psi 1, you call as psi 2 and psi 3, and this is E1, this is E2, this is E3. This equation that we have, H psi n is equal to E psi n, is to obtain all these things generally by proposing a general series, but you remember that we are obtaining the corrections to each and every eigenvalue. When we change n from 1 to 2 we get the correction to the second eigenfunction. When we change n from 1 to say 5 we get the corrections to the fifth wave function, and so on, and likewise for the energies. So this is a symbolic way of writing the equation and obtaining the solutions. Okay. So we shall now go back and rearrange these things, the equation in powers of lambda. Powers of lambda. Left hand side, if you look at, is H naught plus lambda H1 acting on psi n0 plus lambda psi n1 plus lambda square psi n2 plus so on. So if we write this in increasing powers of lambda, the first term which does not have any lambda is H naught acting on psi n0. The next term is, it's a couple of them in lambda, namely H naught on psi n1 plus H1 on psi n0. You have two terms, the 0 order Hamiltonian acting on the first order correction to the wave function, which we do not know, and the first order, the perturbing Hamiltonian acting on the 0 order correction. We know the Hamiltonian, we know the wave function, therefore this is in principle something that we can calculate. Okay. Here, unless we know psi n1, we do not know how to calculate this, therefore that is the objective. The second set is, second term is lambda square. Again if you look at lambda square, the correction is lambda square term is H naught acting on psi n2, has the same power, and the other one is H1 acting on psi n1, okay, plus lambda cube terms, lambda 4 terms. So this is the left hand side arranged in the increasing powers of lambda. What about the right hand side? Remember it is given by E naught E n0 plus lambda E n1, let me write this clearly, E n0 plus lambda E n1 plus lambda square E n2 plus etc., multiplying the wave functions psi n0 plus lambda psi n1 plus lambda square psi n2 plus so on. So if we write this in increasing powers of lambda, the first term is En0 psi n0 plus lambda times, remember there is an En0 times psi n1 and there is an En1 times psi n0, two terms, psi n1 plus En1 times psi n0 plus let me write that here, plus lambda square. If you look at lambda square, there are three terms. There is an En0 times psi n2, En1 psi n1, En2 psi n0. There are three terms. Psi n2 plus En1 psi n1 plus En2 psi n0. If you go for lambda cube, you will see that there will be more terms, there will be four terms, En0 with psi n3, En1 with psi n2, En2 with psi n1 and En3 with psi n0, and therefore you see right hand side for each power of lambda the number of terms increases by 1. But let us stay with 1, 2 and 3, we will not worry about other corrections. First and second order corrections are the most important in elementary quantum chemistry, so we shall derive expressions for that. Now left hand side is equal to right hand side, so you can take a look at this term. Okay, so I think I have the expressions on the screen, so you can see that the first term, now we are equating the left hand side with right hand side for term by term according to the powers of lambda. That is, the first term is lambda to the power 0, it is independent of lambda. Left hand side, that term is equal to the right hand side. Lambda is arbitrary, we said it is a very small parameter. Therefore the perturbation theory now gives us a handle to organize terms into groups, so that you can see the term H0 psi n0, which is independent of lambda, is equal to En0 times psi n0, which is independent of lambda on the right hand side, and this is of course is what we started with. This is the equation for the eigenvalues of the perturbation free 0 order Hamiltonian. That is what this is. Okay, we started with that, therefore it is redundant. I mean, we are getting the same thing, does not help us much. Okay. But then what we have is a series of equations that we can write down. For the power of lambda there is one equation, and for the powers of lambda square there is another equation, and so on. So if you think about lambda square, let me see if I can use a different color. I guess yes, I can use a different color. Let me use that. Okay, so let us take the first order term in lambda. Okay, this is H0 acting on psi n1 plus H1 acting on psi n0, and that should be equal to the same power of lambda here on the right hand side, which is En0 psi n1 and En1 psi n0. Okay, so that is the second equation, which is the first real one that we need to solve, because the one in yellow is of course we already know, that is the proposal we started with. What about the third one? Well, the lambda square term, if you take care of that, you see on the left hand side we have H0 on psi n2 plus H1 on psi n1, and on the right hand side we have the three terms on lambda square, which is En0 multiplied by psi n2, En1 multiplied by psi n1, and En2 on psi n0. Okay, so now you understand that there are infinitely many equations if we go on with many powers of lambda, infinitely many powers of lambda, and therefore we have to sequentially solve these equations. And what is important is that the first equation, the one in green which we have to solve, contains psi n1 and psi n1 and En1. Therefore, by solving the first equation, it is possible that we will get the solution for En1 and psi n1. By solving the second equation involving psi n2 and the known, the previously obtained solution for psi n1, it is possible that we will get, when we write the lambda square equation, we will get a solution for En2 and psi n2 and so on. Therefore, you see perturbation series essentially tells you step by step to obtain the solution. So at this point, let me take a short break. We will come back and write these equations, then use the properties of the orthogonalization and normalization of these wave functions to actually extract the values for En1 and psi n1 in this lecture, and in the next lecture we will obtain the values for En2 and psi n1 again. Okay, we will have a break for about 10 seconds. Now we will write the equation and make use of the properties of the orthogonality and the normalization of the wave functions. So the first equation that we had in green that we wanted to solve is H0 on psi n1 plus H1 on psi n0 is equal to E n1 psi n0 plus E n0 on psi n1. Okay, is that what we have? E n1 on psi n0 and E n0 on psi n1, yeah, that's correct. And this is H0 psi n1, H1 psi n0, yeah. Okay, so let's now do the standard trick that we do in quantum mechanics when we have operators and wave functions. We want to take matrix elements out of it, or we want to get numbers out of it. So let's multiply both sides by psi n0 star and integrate with respect to all the coordinates which are present in the system, and psi n, the wave functions are expressed in terms of these coordinates. So if we do that, we have the equation, namely integral psi n0 star H0 psi n1 d tau plus integral psi n0 star H1 psi n0 d tau, that is equal to integral En1 psi n0 star psi n0 d tau plus integral En0, which is a constant, times psi n0 star psi n1 d tau. So what we have done is multiply, integrate. By what function? By the same wave function psi n0, the same psi n that is there in this equation, the equation that we wanted to solve. Okay. We can do either multiply this with psi n0 or with any other psi which is not corresponding to this n, psi m0. I mean, you know that these wave functions are all non-degenerate, they do not have the same energies. Therefore, if you want to solve this equation and you say multiply by psi n0, you may ask the question, why psi n0, why not by some other psi n0, some other psi m0? Yes, we will do both. The first one is to use the same wave function and get the first order correction to the energy in the next step. And when you multiply by wave function which is not the same as the n, you will get the first order correction to the wave function, and that we will do if we have time today. Okay, so now you can compare this. You know, the H0 can act on the right to give you the whatever the energy is, but we do not know the function on the right. But H0 can also act on the wave function to the left, because the Hamiltonian is Hermitian. Therefore, the H naught acting on psi n 0 star will give you the corresponding energy E n 0, which is real, and therefore this will give you the solution E n 0 times integral psi n 0 star psi n 1 d tau, okay, plus you have psi n 0 star, we will write this as is H 1 psi n 0 d tau is equal to integral, we can take the energies out, energies are constants, they are independent of the coordinates, therefore you have E n 1 and the integral is psi n 0 star psi n 0 d tau plus E n 0 integral psi n 0 star psi n 1 d tau. Okay. Immediately you recognize everything that you need to, namely this is equal to 1 because of the normalization of the wave functions, okay, and I think we had the green earlier, this quantity on the left hand side is exactly the same on the right hand side as well, therefore you can cancel these two things, okay, and you can see that there is one equation, namely for the first order correction to the energy E n 1, look at it carefully, the first order correction E n 1 therefore is whatever is left on the side, which is this one psi n 0 star H 1 psi n 0 d tau integral psi n 0 star H 1 psi n 0 d tau, okay. We know H 1, we know psi n 0, we know psi n 0 star, and therefore now we can calculate E n 1 on the basis of quantities that we already used to define our problem, and the first order correction is the average value. Please remember these wave functions are normalized, and therefore what you have here is the average value of the perturbing Hamiltonian in the nth 0 order state. The other terminology for this is that if you write the Hamiltonian in the form of a matrix using all these wave functions as columns and rows, then this is called the diagonal matrix element of the perturbing Hamiltonian in the eigen basis set of the 0 order Hamiltonian. If that is long, let us write it down. Okay. The integral psi n 0 star H 1 psi n 0 d tau is the diagonal matrix element of the operator H 1 is the nth diagonal matrix element, okay, of the operator H 1 in the basis set of psi n 0. So if you remember, the matrix representation for the Hamiltonian or any operator A is, if you have a set of wave functions psi n psi 1 0 psi 2 0 psi n 0 and so on, and you have psi 1 0 psi 2 0 psi n 0. Please note that the matrix elements are written by psi 1 0. Now I will use the bracket notation H psi 1 0, and if I use the bracket notation I must keep this as the bra states and these as the ket states, these as the ket states. This is the first diagonal matrix element. The next matrix element is psi 1 0 H psi 2 0. This is the 1 2 element, this is the 1 1 element, and so on. And what about this one? This is psi 2 0 H psi 1 0. This is psi 2 0 H psi 2 0, and any one of these is nothing but the integral psi 1 0 star d tau H psi 2 0 d tau, sorry, psi 1 0 star tau H psi 2 0 tau d tau, the integral. It is the same thing that is written in the form of the bracket notation, and you can see that the third element is psi 2 0 H psi 3 0 and so on. So this is the 2 3, this is the 2 2, this is the 2 1 following the matrix notation, and therefore what you see here is this integral psi n 0 star H1 psi n, this one is the nth diagonal element when we write H1 and we write H1 H1 H1. So this is the nth matrix element, diagonal matrix element somewhere here. Okay. Therefore, the first order correction to the first state, the first energy, is the first diagonal matrix element, the eigenfunction corresponding to the 0 order state and the Hamiltonian H1. The second is that of the second, the third is that of the third. So this is the simple result known as the first order correction to the energy. Two ways of writing it. You have written this in the form of psi n 0 star H1 psi n 1 psi n 0 d tau, and this is what is called as En1, and the other way of writing this equivalent is that psi n 0 H1 psi n 0. Okay. So we know. Now we would like to find out what is the first order correction to the wave function psi n1. Okay. What about that? Now again go back to this equation which was the one that we solved. The one in the green. H naught psi n1 contains the psi n1 obviously, and on the right hand side the corresponding quantity also contains psi n1. So we would like to find out what is psi n1. I mean, how do we obtain the corrections to psi n1 through this process? Now here I have to use the fundamental processes of, I mean the principle of quantum mechanics, that if you define a basis set for your problem, we have defined the basis set for our problem as the wave function psi n zeros. If you define a basis set, then any arbitrary wave function that we want to find out can be expressed as a linear combination of the elements of the basis set. Therefore, if you want to know psi n1, it is possible for us to write psi n1 in the form of a linear combination of all the basis functions psi 1 0, psi 2 0, psi 3 0, etc. Therefore, in principle we may want to do the following. We may want to write psi n1 as a linear combination including the psi n0, like what I would do is, let me rewrite this in a slightly different way. Okay. Sum over n equal to 1, say not 1 n, let me see. m equal to 1 to infinity a m n. Let me see if I have what notation I have used in the notes is that. Okay, I have used n k, so not m, I have not used m in my print notes, so I have used the symbol k. So it is a n k psi k 0. Okay. Psi k 0. Okay. Now, only one thing that needs to be taken care of is that this is fine, but why include in psi n1 the quantity a n n psi n0? Why include that? We do not need to, because if you remember the correction to the first order wave function, if you look at, let us go up a little bit. We have written the wave function psi n1, which is now writing, we are writing the correction to this term, we are writing the correction to this term, okay, as a linear combination of all wave functions including psi n0, but please remember psi n0 is already there in this expansion as the leading term. Therefore, it is only appropriate for us to write this by saying, by excluding the term k not equal to n, that is, we will not include that, which is a way of saying a n1 psi 10 plus a n2 psi 20, but when it comes to the term, it is n minus 1 psi n minus 1 0, and the next term that we have is a n plus 1 psi n plus 1 0, and so on. Therefore, we will exclude in this summation the basis function corresponding to the 0 order basis function of this, namely k not equal to n. So this is the proposal that we have to make use of, namely psi n1 is equal to sum over k not equal to n a n k psi k 0. Okay. If we use this, and now we will go back to the equation for the psi n1, namely E n1 psi n0, sorry, the Hamiltonian operator was the one that we need to put on the left hand side. So we have H1 psi n0 plus H0 psi n1 is equal to E n1 psi n0 plus E n0 psi n1. Okay. That is the equation we want to solve. H0 psi n1 and H1 psi n0 E n psi n E n0 psi n1, yes. Now substitute in here the expression that we have just now obtained, this one, namely psi n1 in terms of this, we will bring that in here. Then the equation is H1 psi n0 plus H0 sum over k not equal to n a n k psi k 0 is equal to E n1 psi n0 plus E n0 sum over k not equal to n a n k psi k 0. Okay. Therefore, the task of finding psi n1 psi n1 is now the same as the task of finding the coefficient a n k, all of them, because we know psi k0 anyway for the entire basis set. So we have only transformed the task of getting the wave function in terms of getting the linear combination coefficients, and this now, having substituted this, now we will multiply this equation by this a wave function which is not equal to the n. Let us use psi m0 star, multiply it on the, multiply this equation with psi m0 star and integrate it d tau, both the left hand side and the right hand side. Let me write the equation. Because of the time running out, what we will do is we will solve the equation and obtain the first order correction to the wave function and the second order correction to the energy in the next lecture, and then also use some examples to highlight or to apply these two results, namely the first order correction to the energy, second order correction to the energy, etc., for some of the model systems. Okay. So let me write the last step, namely integral psi m0 star h1, okay, you have to have that, and also the caret h1 psi n0 d tau plus integral psi m0 star h naught. So let me just write this by taking the coefficients and the summations out. We will write the summation term k naught equal to n a n k, and then write the integral, namely psi m0 star h naught psi k 0 d tau, and on the right hand side what we have is E n1 sum over, sorry, E n1, sorry, there is no sum, integral psi m0 star psi n0 d tau plus we have sum over k not equal to n a n k E n 0, and then the integral, namely psi m0 star m0 star psi k0 d tau. Okay. So let us, let's check that I have not made any mistake here, namely psi m0 star h1 psi n0 d tau a n k psi m0 star h naught psi k0 d tau is equal to E n1 psi m0 star psi n0 d tau and a n k E n0 psi m star psi k0 d tau. Okay. So let me conclude by saying that this is 0 due to orthogonality of the wave function. We will continue from this equation and then derive an expression for the coefficients a and k, and once we know the expression for the coefficient in terms of quantities that we can calculate, we know the first order correction to the wave function, and that can be used to obtain the second order correction for the energy and so on. So this lecture will have to be read in tandem with the next lecture in order to understand the first and second order corrections together. Until then, let me say thank you and see you later.